All right, now that we have done some basic definitions about the porous solid, we can go ahead and try to obtain what are the equations of poroelasticity. And in order to do that, we will start with an analogy. And this is going to be based on a non-porous solid to get started. What is the internal energy of a non-porous solid? If we are specifically talking about mechanics, and then the internal energy is going to be the strain energy. And this strain energy, we can break it in two parts. The part which depends on the volumetric strain, for example, if I had a solid, I could apply a stress that makes it smaller. And that's going to depend on the level of stress and the change in volumetric strain, where here Sm means the mean stress. For example, S11 plus S22 plus S33 divided by 3. And remember that this epsilon is the volumetric strain. So if I want to add work to this solid, I can add work by straining the solid. So this is a differential amount of work. Okay, solids also can bear shear strains and shear stresses too. So I can partition this energy of the solid into volumetric strain and shear strain. And for example, if I apply a shear, I could distort the shape of this solid like this one, and then the additional energy that I put into the solid is going to be proportional to the shear strain Ij times the strain or change of strain in this case Eij, where Sij in this case is S12, S23, and S13. Remember that we're dealing with the solid in 3 dimensions, even though we are drawing this in 2 dimensions. And also, these are the shear strains 1, 2, shear strain 2, 3, and shear strain 1, 3. Here, just to follow also the convention of the book, I'm using the book from Cusi. I'm using this E, but this you could also think of this in terms of just the regular epsilon that we have used before. It's just a shear strain. Okay, so this would be then the additional strain energy that I can put into a non-porous solid. All right, so let's see now what would be the case for a porous solid. So for a porous solid, now I'm going to have pores, right? So let's simplify this porous solid to the maximum, and we just have one single pore. And let me add also summation sign here. And here I'm going to have also this porous solid, and you will see that I'm going to have one more term over here. So let me just go ahead and add this one. All right, so similar to what we had before, we're going to be able to compute what is the additional work I put into this porous solid. And similar to the case before too, this is going to be proportional to the mean stress times the change of volumetric strain of the entire solid. For example, if I were to apply a compression, then this solid will change size, but also the pore would change size. Next term, similar to before, here I'm going to have the shear stresses times the shear strains, and this is going to be very similar to what I had before. And if I apply a shear, this is going to make the solid distort, and probably the pores to distort too. But do you think the shear is going to change the volume of the pores, shear by itself? The answer is no, and we'll see that also later on how that impacts on our equations. All right, here now in the case of the porous solid, we're going to have an additional term. And this additional term comes from the possibility that I have a deformation of the solid which is just caused by the increase in porosity caused by a change of pressure. And this is going to be without a change of the bulk volume. And in this case, this additional work or energy, internal energy of the solid, is going to be proportional to pressure P and proportional to the change in porosity. All right, so this is the additional term that I needed in order to take into account porosity. Notice that this Lagrangian porosity that we have defined in the previous lecture also can be written in terms of the variation of porosity itself. And that's the one that we're going to use later on, so just let me clarify that these two are going to be the same mathematically, not physically, but mathematically they are going to be the same. Okay, let's continue then, and let's try to work on this equation that we have right now. And let's try to understand what we have in here and how we can use this equation in order to get to the equation that we want. All right, let's concentrate on the first term and try to understand what that is. And for that, let me make a plot where I have volumetric strain on the x-axis and mean stress on the y-axis. If I have a linear elastic material, the relationship between mean stress and volumetric strain is a line, and it is linear, right? And if, for example, I want to take an element of a solid from zero strain to some non-zero strain, let's say somewhere over here, the work I have to do is going to be the area under this triangle. This is similar to a spring. If you remember, for a spring, if you want to calculate what is its potential energy, that depends on the force and the displacement. All right, let's see a few more things that are going to help us to calculate that volume. The slope of this line is actually the bulk modulus K that links volumetric strain and mean stress. And this triangle is going to have a height and it's going to have a base. And as we said, the work is going to be equal to the area of that triangle, and the area of that triangle is going to be the base times the height divided by 2, where the base, notice, is just going to be the strain times the height, which is going to be the strain times the bulk modulus, right? That's because of the definition of the bulk modulus. Well, let me write the definition of the bulk modulus here. The bulk modulus is defined as the change of mean stress divided the change of volumetric strain. So from here, if I want to get the height, I just need to multiply strain times K. So at this point over here, this is going to be the strain times K, and all of this divided by 2. And this is going to be equal simply to 1/2 of K times strain, volumetric strain squared. And this is very similar to the equation that you know, as I was telling you before, for the spring, where the potential energy is proportional to the stiffness and also proportional to the square of the deformation. Also, to play a little bit more with this equation, and before we go into the analogy, notice that if we wanted to take the partial derivative of this work with respect to strain, what I get is derivative of epsilon is just going to be actually of epsilon squared, it's just going to be 2 epsilon, and this is just the 2 is going to cancel, so this is going to be K times epsilon, and we know that K times epsilon is actually the mean stress Sm. So this is our proportionality. Sm is equal just to K times epsilon. Okay, so this work, if we wanted to integrate it, then it's just going to be equal to 1/2 of K times the total volumetric strain squared. All right. I hope that was clear, because now we're going to go to the next step, which is a little bit fuzzy, and we're going to do a proof by analogy. That if a mathematician will see me doing this, probably will be very upset. But let's just go ahead, because this is going to save us significant time, and proceed with this proof by analogy. Let me move this over here, just to make a little bit more of space. Okay, in this proof by analogy, what I'm going to do is I'm going to define what is called the Helmholtz free energy of the solid, eta S, and the total energy, not the differential, is going to be, as we saw in this demonstration just for the volumetric strain part, is going to be 1/2 of K times the volumetric strain squared, where K, remember, is the bulk modulus. All right, let's go with the next term. Actually, what we want to do is to rewrite this equation for these 3 terms. The next term is going to be very similar, but is going to relate shear strains and stresses. So similar to what I did in here, I'm going to assume linear elasticity and also an isotropic solid, and this is going to be proportional to the shear modulus times the product of the shear strains. So this is going to be epsilon 1,2 squared, epsilon 2,3 squared, epsilon 1,3 squared. And I just summarize it into one term just by writing this, where G is the shear modulus. All right, nothing new so far. And notice that this is in strain squared, similar to what I have over here. These are going to be the new terms. The first one is going to be a constant that I would call alpha, and links the volumetric strain and the pore pressure. And the second one is going to be similar to what I had in the first 2 terms, 1/2 of 1 over n, where this is just going to be a constant, times the pressure squared. And notice again that this is a constant. Let's call it constant number 1. And also this one is a constant. Let's call it constant number 2. What this equation is telling you is that the internal energy of this solid is going to be proportional to the volumetric strain of the bulk solid, the shear strains of the solid 2. That also is going to be proportional to the interaction between the volumetric strain times the pressure. Notice that pressure times strain we saw before, it's actually energy, and also depends on the energy of the fluid. So this is the pressure squared. This is just the component of the energy of the fluid itself without interaction with the solid. Okay, let me summarize all these terms with their physical meaning. So we said that this is going to be, let me do it in colors. This is going to be the term of the bulk volumetric strain. This is going to be the term of the shear strains, and these are going to be the two terms that depend on pressure. All right, and this was our proof by analogy. If you want to see a rigorous proof of that, I recommend that you check the book of trying to remember the exact name, Physics of Porous Solids by Olivier Cussy. All right, so with this equation, what we're going to do now, it's something similar to what we did before with our equation of just the potential energy for the volumetric strain. And we're going to take partial derivatives. And I'm going to take partial derivatives of this Helmholtz free energy, eta S, with respect to first to the volumetric strain of the porous solid. And let me bring this equation in there. As you can see over here, the only terms that are including this volumetric strain are the first and the third one. And when I take the derivatives, this is going to be equal to K times volumetric strain from the first term. And here, this is just going to be alpha times P, which is the pressure. And if I go back also to the equations that I had before, from this definition, you can also notice that if I take the derivative of the internal energy with respect to the strain, volumetric strain in this case, this is just going to be the mean stress. Okay, let me write that M again. Let's go with the second one. We're going to take now the partial derivative of the Helmholtz free energy with respect to the shear strain. And notice that the shear strain, the only term that we have in here is the second one. So, and this is going to be squared. So when I take the derivative, that actually is going to be 2 times G times that shear strain. And again, if we check the equations that we had before, this is going to be equal just to the shear stress, Sij, little s. This is a little s, that's a big S. And finally, I'm going to take the derivative of this Helmholtz free energy with respect to pressure, and also I'm going to multiply that times -1. And what I would obtain after doing the math, notice that the terms with pressure are going to be the the third and the fourth one. And notice that we have a negative over here. So this is going to be equal to alpha times volumetric strain times the derivative of p squared. That's going to be 2p, and it's just going to be 2p divided by 2. That's going to be p. It's just going to be p divided by n. And this is going to be equal to, by analogy with the first equations that we wrote, this is going to be equal to the change of porosity. And these three equations are the three basic and fundamental equations of poroelasticity, where we have the equation for total stress as a function of pressure and strain. And if you go a little bit further into this, total stress minus a pressure, if you remember, that was an effective stress. And the effective stress in this case is going to be this. It's going to get clearer later why this is an effective stress, where this is a total stress and this is the pressure part. And remember that in this poroelasticity part, where you are using the general mechanics convention, so a compression is going to be negative. But don't worry much about the signs right now. We'll come back to that later on. And this equation, let's put names on this. Equation number 2, number 1, number 2, and number 3. This is the Biot effective stress equation. And this parameter alpha, as we're going to see, is the Biot coefficient. Let's we'll show how to measure and how to define the Biot coefficient later on, but for now let's just keep the discussion to this. What you should notice now from these equations is that these two coefficients, where this one is called the poroelastic modulus, are two new coefficients that we didn't have so far. And so that's something that we're going to have to determine. For example, we know what K is. K is the bulk modulus, and we know how to measure that. We know what G is. G is the shear modulus. But now we have these two new coefficients or material parameters, which are alpha, which we don't know what that is yet, and also N. And we don't know what that is too. And what we're going to do next is to find out what those two are. All right, so let's go ahead with that. In order to obtain these two coefficients, we're going to have to perform two experiments. And these are going to be virtual experiments or thought experiments. First, let's clarify what K is and what also it's a jacketed test or a jacketed loading. Notice that now that we have a porous solid, if we want to load it and we don't want if we, for example, load it with a fluid, and if we don't want the fluid to get to the pores, what we're going to have to use is some sort of membrane that covers the the pores of the porous solid so that the fluid doesn't get in. This would be a membrane or also a jacket. That's called the jacketed loading. And for example, if I apply an external stress or an external pressure, then what I'm going to get is the deformation of the entire porous solid is going to depend on the volumetric strain, as we stated before. If this is the mean stress, mean total stress, and this is the volumetric strain, then assuming linear elasticity, the slope of this line is going to be the bulk modulus of the porous solid, or also I could call it the K jacketed. Notice that because of the pores, and we're assuming in this case that we don't have any fluid inside, so the pores can compress without any increase in pressure, the presence of the pores are going to make this solid to be more compliant than if it wouldn't have any pores. And the higher the porosity, the more compliant the solid is going to be. That's why it's important to put this jacket and this membrane around it so we can measure that compliance of the porous solid without any fluid inside. All right, so I hope that this kind of test was relatively straightforward to understand. Now we'll go to another kind of test, which is the unjacketed loading. And this unjacketed loading, it's I wouldn't say more difficult to understand, but just something that we are less used to see. All right, in the unjacketed loading, as the name says, we're going to have a solid which has pores inside. I assume that these pores are all connected to each other and are also connected to the outside or to the surface of the rock, so that if I apply the pressure, external pressure with the fluid, the fluid is going to get in, because now I don't have any jacket. And this fluid is going to have a pressure P. And since I don't have any jacket, then as we said, the fluid is going to get in, and as it gets in, also is going to apply pressure on the pores of on the walls of the pore. That same pressure P is going to go through the pores, get everywhere, fill everywhere, and apply the same pressure that I have on the external walls. I'm going to have it inside the pores. And let me go also pick another piece of rock over here. Let's say that we're trying to understand what the state of stress is in here. Notice that we have the pressure from the pressure on the bottom, but also since this one is pressurized with pressure P, it's also going to have a pressure from the top. All right, so I think I'm done with my schematic. Let's go now to the equations, and let's use equation number 1. All right, equation number 1 tells me that this equality is going to hold based on what we derived before. And now the mean stress that I'm applying is equal to the pressure, exactly to the pressure. That's going to be the total stress. And since in this case the pressure is going to be a compression and we are using the regular mechanics convention, then this is going to have a negative sign and it's going to have to be negative P. Let's solve for the volumetric strain. Now the volumetric strain then is going to be, I'm going to pass this term into the other side, right? And this is going to be P, and I'm going to have a negative over here, -1, and this alpha is going to be now positive, and I'm going to divide this by K, and I can rework this equation to a more convenient way to express it, and tells me that the volumetric strain is going to be, let me take the negative sign out of here, and this is going to be P 1 minus alpha divided by K, where K, remember, is the bulk modulus of the porous solid or the jacketed volume. Okay, let's try to understand what this equation is telling us. What this equation is telling us is that if we apply a pressure, then the solid is going to contract. And that kind of makes sense. But we're going to go one step further here. And we're going to see what the strain of the solid part is going to be. All right, since I'm applying this pressure, which is the same in all directions, and it gets into the pores, into all the pores, and this solid that I'm dealing with is isotropic, then I hope that you can see that we saw that the entire solid is going to shrink, but also the solid itself is going to shrink. And how much it shrinks is going to be related by the pressure. For example, if I take this piece of solid over here, I know that it is holding the pressure or stress from the bottom applied on the surface, is holding the pressure from the pore applied on the top, and it's also holding the pressure and stress which is going from this side from right to left and from here from left to right. So at the end of the day, this solid has a compressional stress which is equal to P in all directions. And because of that, the strain of the solid is going to be equal to P divided the bulk modulus of the solid part. And we're going to go into one more step here that requires a little bit of trying to picture this example and trying to imagine what is going to happen when it deforms. And notice that this entire volume is going to shrink a certain amount. And that shrinkage is going to be related about how much the solid part shrinks. But the solid part shrinkage, we saw that is going to be proportional to the pressure and inversely proportional to the volume of the solid. But if you look at this case is going to repeat everywhere. The shrinkage of this solid is going to be the shrinkage of a solid over here and of a solid over here, of solids around the pores. And what that means is that since the shrinkage is going to be the same everywhere, actually the volumetric strain of the porous solid itself also is going to be the same as the shrinkage at any point. And so if I state that mathematically, that means that the volumetric strain is going to be equal to the volumetric strain of the solid. And if I relate the two equations that I had above, then the result is going to be, let me get rid of the negative signs. This is going to be P1 minus K divided, 1 minus alpha divided by K is going to be equal to P divided by Ks. And these P are going to cancel out. And what I'm going to get solving for alpha is that alpha is going to be equal to 1 minus K over Ks, where alpha is the Biot coefficient and the Biot coefficient is going to be 1 minus the bulk modulus of the porous solids, the jacketed modulus, divided the bulk modulus of the solid part. So just to clarify this, remember this is the bulk modulus of the porous solid jacketed, and this one is the bulk modulus of the solid skeleton. There were quite a few assumptions in getting to this derivation. And remember that one of those is that all the porosity is connected. If the porosity is not connected, then this is not going to work. But we'll see also that a little bit more in detail later on. All right, so the question here is now, which one is bigger? The bulk modulus of the pore solids with the pores or the solid without the pores? And the answer is the bulk modulus of the porous solids with pores is smaller because it has pores inside and are compliant than the bulk modulus of the solid itself. And as a result of this, alpha is going to be equal or smaller than 1. And of course, it's going to be valid for Ks, which is equal or larger than K. All right, so we have found out now what our Biot coefficient is, and this is the Biot coefficient, remember, for a solid. And let me write it down here because these are the assumptions that we have in order to derive this equation. This is an isotropic elastic solid, and that's the solid skeleton. And also we're assuming that we have a fully connected porosity. And with those assumptions, we were able to find out what the Biot coefficient is. I'm going to show just in a bit typical values of the Biot coefficient. But before we do that, let's go ahead and answer what the other parameter is. The parameter which is the poroelastic modulus n. All right. So let me come back over here, and for the same experiment, now let me use equation number 3. And equation number 3, let me make some space. It's not letting me scroll down. Okay. All right, so equation number 3, it's about the change of porosity, and this was the equation I had, and now I know what the volumetric strain is going to be. So alpha times the volumetric strain for this experiment, I have seen that it's going to be equal to this amount, which depends on the pressure applied and the modulus of the solid part, plus Pn, and that's going to be equal to the change of porosity. And from here, I can also come back to the concept of the porosity strain, which is the change of porosity divided the initial porosity, and try to find out what is that value. Similar to what we said before, in this experiment, if all the solids shrink the same amount, that means that the pore space is also going to shrink the same amount. And that same amount is this amount. And so that porosity strain is also going to be equal to P divided by Ks. So I can combine now these two equations, and I can write the following. So the first equation is just a repetition of what I have above, plus P divided by N. And now I have here the change of porosity, and the change of porosity is going to be, according to this equation, the pressure divided by Ks times -1 times the initial porosity. And notice that the pressure is going to cancel out from all the terms. And what I'm going to obtain finally is that this poroelastic modulus N is going to be equal to the I forgot to close the parentheses here. Okay, that makes sense now. Yes, and this is going to be equal to the Biot coefficient minus the initial porosity divided by Ks. And for this isotropic solid with connected porosity, I can calculate what that material parameter is. All right, now that we have the two parameters, let's just complete the description of the solid with a few more things that in order to close this topic. First, let's just remind ourselves that this is going to be also what is called the second poromechanical parameter, or the second poromechanical modulus. Since it is a modulus, notice that it cannot be negative. So, you know, there is no such thing as a negative Young modulus or a negative bulk modulus. So since this is a positive amount, Ks, in order for this equality to remain positive, that means that if N is going to be positive, then this implies that the Biot coefficient is going to be higher than the initial porosity, and that's going to imply a constraint on the Biot coefficient. If we join this condition that we just found here to the one that we had before, that alpha has to be equal or less than 1, we can write down this inequality that the Biot coefficient is going to be larger than the initial porosity and is going to be smaller than 1. Okay, so with these two tests, we have seen what these two poromechanical parameters are. And again, in summary, these are the Biot coefficient and the poroelastic modulus or second poromechanical modulus 1 over n. I need these two in order to fully utilize the equations of poroelasticity. So these two additional parameters, then we have a solid with connected porosity, it's isotropic, it's made by material with all of the same rock, then I can find out what those two are. However, in real rocks, the conditions that I have stated are not going to hold. Real rocks are not going to have all its porosity always connected, are not going to be isotropic, and also are going to be heterogeneous. So probably this bulk modulus of the solid is going to vary from place to place, and some of the tricks I use in order to develop these two equations, they're not going to be valid. But anyway, these two equations are very useful in order to understand a little bit better poroelasticity. And for example, here I have a summary of poroelastic parameters from a compilation from tests done here in my laboratory at UT Austin, and also from the book from Unjacketed et al., where we can see, let's go to the Biot coefficient. For example, we can see the value of the Biot coefficient as a function of porosity. And we can see, as we stated in our equations, that this Biot coefficient is smaller than 1, that it is higher than porosity, and in general, this relationship shows that the smaller the porosity, the smaller also the Biot coefficient is. We can also see also some relationships over here that, for example, let's see, there are some things that we don't know yet, but for example, here we have the pore modulus for these different rocks as a function of porosity. And also we can see that the pore modulus tends to increase as the porosity decreases. In general, these poroelastic modulus are going to depend on the properties of the rock itself, but also on the porosity and how connected it is. And those two are going to define what the poroelastic response of the rock is. So I think I had a few more plots here. I think I like this one too. It shows the Biot coefficient as a function of permeability for these rocks. And you can also see in this example that you might have rocks, for example, with more or less the same porosity or the same permeability, but that doesn't mean that they're going to have the same Biot coefficient. There is no unique relationship between the total porosity and the Biot coefficient. And again, let me just repeat one more time that in general, the tighter the rock, for example, shales, low porosity carbonates, low porosity sandstones, are going to have a lower Biot coefficient than looser materials, like for example, a frio sand, an unconsolidated sand, or for example, a high porosity mud rock. In the limit, for example, for soils, a typical assumption is that Biot coefficient is equal to 1, but that's something that we cannot do with tighter rocks.